have done. I was thinking of a few questions that I think Aristotle wouldn't appreciate very much. This thing about the middle term, all birds fly, ostriches are birds, birds fly. You might say, well, the problem was when you said all birds fly. Yeah. Because they don't. So, that's not a true statement. The thing is, though, that how would Aristotle deal with the need to change the language? When you've got a concept that you don't already have a way of describing, you end up always describing it in contradictory ways. Opposites exist. This maximum minimum was an example, but here's a few other ones. How many sides does a circle have?
360?
Only one.
Infinite. One, therefore infinite. It doesn't have anything.
Well, sure, yes, it seems that it would be difficult to choose among these answers unless you were to say, well, really all of them are good, because, although in a way that none of them is really right. I mean, in other words, a circle doesn't have one side in a way that excludes it having an infinite number of sides. It doesn't have no sides in a way that excludes it having one. I mean, you might say, well, it doesn't have any sides. It's round. Sides are flat. It doesn't have any sides. You might say it has...
You define sides as flat.
Yeah, or you might say, well, it has one side. Well, you might say it has an inside and an outside. It's got two sides. You want it to be tricky, but well, the front side, the back side, right. However you're looking at it, there's the left side, the right side, the top and the bottom. So, it's when you ask a question that doesn't really make sense, you get more than one answer, because the question isn't appropriate for understanding the thing that you're talking about. So, how about another one? There's this story about Archimedes, there's this eureka moment where he's in the bathtub, and there was this problem of trying to determine whether this gold bauble or crown, I don't know, whatever it was, that was made for someone or another. The question was it really pure gold? Was there some other metal mixed in it? And Archimedes thought about putting something in water, and you could measure how much water it displaced, how much the water in the bathtub went up, or if you had it in a jar, you could measure how high the water went up. And that way you could figure out the volume of a strangely shaped thing. You could weigh it. So you could get its density, the relation between its heaviness and its size. And you could say, well, does it weigh as much as gold or is it lighter? And you could figure out how much of it was gold versus silver that way. So I just looked up on Wikipedia, and I found that the density of gold is 19.3 grams per cubic centimeter. The density of silver is 10.5 grams per cubic centimeter. Can anybody tell me, I sort of ran out of time, what the density of carbon is? Feel free to use your phone if you want.
In which form?
Just like gold or silver, they've got densities, so yeah, what's the density of carbon?
Probably less. Graphite?
Carbon.
Carbon.
Well, gold and silver, they're elements, right? So, carbon's an element. What's its density?
2,000, but this is kilograms per meters cubed. So I don't know if it works the same.
What did you get for that?
2,250.
So that'd be like 2.25. Did anyone else get the same?
Kilogram per meter cube, yeah. 2.0 kilogram per meter cube. Oh, what are the units you're looking for?
Yeah, whatever. I mean, grams per cubic centimeter would be nice. If you get kilogram, 2.2670. Any other numbers?
Because there's different density for graphite, diamonds, and all forms of carbon. So could be
right.
different numbers.
Well, that's a trick, right? So there isn't an answer to that question, or there's multiple answers to that question, and it tells you something about carbon that's not true about gold or silver. I mean, gold's gold, silver's silver. Carbon, diamond versus graphite. So the word carbon, gold and silver sort of have they're words that are fulfilling two meanings. They're chemical elements. They're also physical metals. Carbon, people were immediately saying, well, what kind of carbon, right? Carbon's a chemical element. It's not a physical material. Graphite's a material, a physical material. Diamond is a physical material. You could go back to the Stone Age and say, you know, I mean, diamonds aren't just laying on the ground, but if they were, diamond, graphite, those would have words. There would be no word for carbon. You didn't have chemistry, you wouldn't have any idea that a diamond is the same thing as a piece of coal, would you? They're just not alike at all, really. So there's another example where the question doesn't have an answer, or it has multiple different answers, and that lets you realize that the way you were thinking has some room for improvement. If you ask what's the density of carbon, it's just not a good question.
I was just thinking, like, is there anywhere that Aristotle knew these questions just couldn't be answered, or just ridiculous? Because like that has to come to his mind eventually.
I mean, I don't know how
Someone
you
has
could,
to.
with like a straight face, do this thing about our sense of touch is what makes us intelligent. I don't know. To me, that sounds like the great lie or whatever. It's like, look, if people will go with this, you know, it's like just demanding people accept all of that, and it's like, how far can you push them? You know, here, eat some shit. You know, but feel it first. Here's a couple other ones. The atomic mass of chlorine. Kind of a weird one. If you looked at the weights of how about uranium? He said, what's the atomic mass of uranium? How much does an atom of uranium weigh? Does anybody know the answer for that one?
Yeah, we have to look at the isotope.
Which isotope, right? Now, no one would have asked that in the year 1900 or in the year 1890. That wouldn't have come up. It's, here's some uranium, and what does it weigh? There weren't different isotopes. Chlorine, why does it weigh 34.5 instead of a nice even number like most things do? Who knows? Maybe there's something very weird about chlorine. So again, yeah, right, it's a word that doesn't apply anymore because you're missing the concept of isotopes. How many terabytes of storage are in your brain?
I just upgraded.
Oh, you did? Oh, I got an SSD one. It's amazing. I remember things so quick now. It's good. The only trouble is once they go, they just go real quick. You know, you lose your mind. So, are you left wing or right wing? Is LaRouche, is he liberal or conservative? Is he Fox or MSNBC? Right? What is conviction or certainty? What does that feel like? What's the image associated with that experience in the mind? Because all mental experiences come with an image, a sensation. Is that a sensation that's like any of the ones that come from your senses? Does justice feel more smooth or more fuzzy?
Feels more purple.
Purple? Right. Yeah. So, you know, so those are some of the examples of the problems with it, the problems with logic, and then the fact that you can't really improve your language if you take that approach. Say, well, we've got ways of talking about things, and they'll serve us forever into the future. We can describe everything and use the language we've got right now, because how could we ever define a new term if it can't be defined in terms of what came before? So think about these examples where you just had to develop a new language. Like you don't say, well, I'll tell you what the density of carbon is. You can't answer that. You realize that it's just not a legitimate question. You got to go somewhere else. So I'm going to play a video now. Actually, unless has anyone seen? I made a video like about a week ago on fusion. Raise your hand if you've seen that. Most people. Okay, enough people haven't that you're going to have to watch it again. So. But you get the unedited version. YouTube censored out the music and managed to remove it, so you get to. Yeah, it had a fake copyright violation problem thing, so you know. There was no actual copyright problem, but they don't know that.
We're getting the uncensored version.
We're getting the uncensored
Okay.
version.
Jason
The,
Ross.
well, the one with music, anyway.
The only way mankind will exist in the future is through the mastery of controlled nuclear fusion. But fusion cannot be understood by enumerating its benefits or by calculating its electrical potential, although it is immense. The new quality of human civilization it will allow can only be adequately understood by looking at it in the long-term context of human development, from the physical world of the Stone Age to the chemical world of the Bronze and Electrical Ages to the nuclear world that we have only just ventured into. By contrasting these stages of physical, chemical, and nuclear, we can understand the profound importance of developing a fusion platform, and specifically one powered by the rare isotope helium-3, found naturally on the Moon, but not on Earth. We'll start by going back in time a few thousand years. Ten thousand years before the present, in the Stone Age, our tools and technologies were material, physical. Many tools were made from rocks, which might be chipped into better shapes, such as for sharpening, and other materials used for construction and tools were those found around us or made from them, such as fiber, wood, bone, shells, mud, and stone. If someone considered what a rock was made out of, the answer would be smaller rocks, and wood was made of wood. The characteristics of objects that were of value, besides food, were what we would call material or physical ones, such as strength, hardness, flexibility, durability, heaviness, size, shape, temperature, and so on. The changes we were able to cause were in large part physical reshaping and cutting and grinding, as well as movement. The simple machines of antiquity, the lever, the screw, the wedge, the pulley, and so on, these are physical machines, which could transform one kind of motion into another kind. For example, lifting a weight could be made easier by using a system of pulleys. More rope is pulled, with less effort, to lift a heavy weight a shorter distance. Or one mass could be used to lift another by using a lever. This table includes some characteristics of the physical world, the kinds of machines we had created, the characteristics of materials that we'd be thinking about, and the kinds of changes that we could bring about. Not included in this table is the application of fire, the use of which absolutely separated the human species as a creative species from all other forms of life. The first evidence for the use of fire goes back hundreds of thousands, or perhaps 1 million or more years. With fire, man could cook new foods to make them edible and safer, harden rocks to make for sharper edges, fire clay, increase the flexibility of wood by boiling, treat textiles to create fabrics. We could see and protect ourselves at night. We could clear land. We could bake. After wood fire, the first change in our power over nature that was of a truly different physical type was seen in the birth of the Bronze Age. The Bronze Age, like the later Iron Age, took its name from advancements in making metals. Bronze is a combination of copper and tin, which requires a new kind of power over nature to create, and the resulting material, bronze, is stronger and more durable than either copper or tin. This is malachite. It's a blue-green rock, and it was the primary source of copper in the Bronze Age. As a rock, despite its unusual color, it's not so different physically from other stones. It's not remarkable by its hardness, its weight, its durability, its ease in chipping apart to make sharp edges, Yet, when a new kind of fire is applied to it, something amazing happens. This new type of fire is that of charcoal. Charcoal is made from wood by partially burning it without air, such as slowly burning it under a pile of earth, as you see here. The resulting charcoal burns both hotter and cleaner than a wood fire, allowing for more convenient cooking than using wood, which creates a ton of smoke. A charcoal fire has the ability to cook malachite and turn this rock into a metal. Let's look at how modern-day researchers have recreated the process. After grinding up the malachite with a stone, they dig a pit, start a fire in it, add charcoal, add the ground malachite, more charcoal, and a top, and blow air into it with a bellows to keep the fire going. After some hours, the process is complete, the pit is reopened, the malachite has disappeared, and copper metal has been formed. This is an astonishing change, absolutely unlike any of the physical changes created before, and far more dramatic than the change of baking bread or of cooking meat. The very nature and material of the rock has changed in an almost miraculous way. It's hard to imagine things that are more different than a rock versus a metal. Metallurgy was the beginning, the first example of what were later called chemical changes. With the development of modern chemistry by Antoine Lavoisier and Dmitri Mendeleev, among others, the answer to the question of what is a rock made of was totally different. No longer was a rock made out of rock. Now the chemical elements, the smallest pieces into which the rock could be broken, including by these new kinds of processes, these elements were being worked out. A rock was now made of silicon and oxygen, in the case of this rock, or copper and oxygen, in the case of this malachite. And these component parts, oxygen, silicon, copper, they had absolutely none of the physical properties used to describe the physical materials they formed. For example, graphite, coal, and diamond, they're very different in their hardness, their color, their density, in almost every imaginable way. Yet these substances are all made entirely of the chemical element carbon. So carbon doesn't have a color. Carbon doesn't have a density. Carbon doesn't have a hardness. What carbon has is a susceptibility of entering into particular compounds with itself and other elements, making materials that do have physical properties. Yet the properties specific to carbon itself are chemical properties, not physical ones. They relate to the kinds of compounds it forms, the ease with which it does so, what ratios it combines with other elements in, and so on. The first chemical machine was metallurgy. The work of transforming rocks into metal was totally different than what could be done with physical machines, with cutting, grinding, pulling, scraping, banging, heating. None of that makes copper. The charcoal fire was pulling the oxygen away from the metal in the rock, in effect undoing the process of rusting, which is the chemical combination of a metal with oxygen. We saw this with the creation of copper from malachite. It wasn't just the heat of the charcoal fire, it's the chemical characteristic of it. Here you see a form of processed iron called taconite, which looks like balls of rust, which is essentially what it is. When it is smelted into iron, it is, in effect, unrusted chemically by removing the oxygen. Around 1700, a powerful new chemical machine was developed and built, the steam engine, which used the potential of coal to change chemically, to burn, in order to produce motion. And now the power of a lump of coal was much greater than its ability to weigh down on a lever or a pulley. It could be burned to heat water, to produce steam, to push on pistons, as in a steam locomotive. Let's compare the physical versus the chemical power of a lump of coal. In order to get the same energy as burning a given amount of coal, you need to have 100,000 to 1,000,000 times as much water flowing through a hydroelectric dam, depending on the height of the dam. This means that the coal is nearly 1,000,000 times more powerful when it's burned chemically than its weight is were it to be used physically. This is the astonishing power, the astonishing energetic power of chemical machines. A whole new vocabulary now exists. Some of these new chemical attributes include valence, enthalpy, and atomic mass. These terms are likely unfamiliar. They relate to the ability of elements to combine, and in what ratios, valence, the heat released or consumed in such chemical changes, enthalpy, and the characteristic mass associated with a certain quantity of an element, determined by how it interacts with other elements. That's the atomic mass. This was a whole new domain of characteristics, and understanding it allowed us to create and understand a whole new domain of changes, including everything from soap to camera film, from cement to gunpowder, superglue, antifreeze, petroleum, plastics, new alloys, tougher steels. Recombining elements could create materials with totally different physical properties than previous compounds the elements had entered into. One particularly dramatic change was the chemical development of nitrogen fertilizers, which are responsible for the lives of a significant portion of the people currently living on this planet. That one discovery, that one innovation, very directly changed the potential global population of our species. This whole world of chemical characteristics, processes, and changes, it required a new vocabulary, and it represented a higher level of power than the purely physical changes of the past, of the Stone Age. To get into the next form of action, nuclear, we'll talk a bit about atoms, which were a contentious development in the field of chemistry. Elements, and atoms in particular, were understood as the fundamental components of matter. Their combinations might change, but the constituent elements and atoms did not themselves change. Take this wood fire, for example. Carbon in the wood combines with oxygen in the air in the burning process to form carbon dioxide gas. The carbon that was in the solid wood is still carbon when it's in the carbon dioxide gas. Well, wood is not a gas, but carbon itself can be in a solid or a gas. Carbon in one compound is still carbon when in another compound, and no techniques had ever been found that could change one element into another, even though alchemists had been trying for a long time to turn lead, for example, into gold. Atoms themselves are considered as a heavy nucleus containing positive protons and neutral neutrons, with a swarm or cloud of negative electrons swirling around it. Chemical reactions and changes are considered to be related to the interactions of these electron clouds around atoms, not the nucleus. Yet the nucleus determined what element the atom was. Understanding of the nucleus moved forward with, you guessed it, nuclear science. You know, we sometimes forget today that the word nuclear means pertaining to the nucleus. You yourself are very nuclear. There are several thousand trillion atoms in your body, and each one has a nucleus. Experiments with radiation, truly a fascinating subject, led to the hypothesis that the nuclei of atoms were themselves sometimes changing and emitting various sorts of radiations as they did so. This was a new kind of change. Physical changes to a rock still make pieces of rock, and chemical changes to a rock may pull apart the elements, but they don't change them. Remember, the copper was already in the malachite. But now, the nuclei, the type of atom, the element itself, was actually changing. Parts of the nucleus were energetically flying off. The most common changes were the nucleus emitting 2 protons and 2 neutrons, together called an alpha particle, or a single electron, a beta particle, or a high-energy light-like ray, called a gamma emission. These names come from alpha, beta, and gamma being the first 3 letters of the Greek alphabet. So the amount of energy that could be given off was astonishing. It overthrew the laws of physics. To give an example, a given mass of radium, which is a very radioactive element, it emits as much energy over time as 500,000 times its mass in TNT. This is a tremendous amount of energy. Remember that the coal has hundreds of thousands times more energy when burned chemically than when simply weighing down physically. And now a nuclear process is about 1,000,000 times more powerful than a chemical one. So overall, there's about 1 trillion times more power in nuclear processes than in physical ones. But this radiation energy is typically released very slowly. It would take 1,600 years for a piece of radium to release half its energy. That's its half-life. This would mean that if you wanted to go off the grid and power your house or apartment with radium, you would need several hundred pounds of radiating radium to make enough energy. Radiation is quite weak, and it's totally unsuitable as a large-scale power source, although radiation energy does power the Curiosity rover up on Mars. But radiation, it's not energetic, it's not very powerful, and it's certainly not how nuclear power plants work. They're not based on radiation. If they were, they'd hardly make any electricity at all. There's another kind of nuclear change we need to know about to understand this. It was discovered that some nuclei, instead of only emitting these puny radiations, would also sometimes crack and split in half, creating 2 new atoms of varying types, along with several neutrons and a tremendous amount of power. This breaking apart of a nucleus is called fission, and it happens spontaneously in some kinds of nuclei. But what made nuclear power possible was the discovery that, unlike normal radiation, which just occurs on its own in certain nuclei, fissions could actually be caused when the nucleus was stimulated by having a neutron smash into it. By arranging enough of these fissile, that's a word that means capable of stimulated fission, by having enough of these fissile nuclei gathered together, a chain reaction process could be made where one fission would cause other fissions with the neutrons it created, which would in turn make more fissions, and so on and so on. This could release a great deal of energy very quickly, and it could be useful for power, unlike natural radiation, which basically makes rocks get warm. This power of fission is what happens inside current nuclear power plants. And except for a few very unusual geological formations, this fission never occurs in nature. It is a specifically human-created form of fire. It is only made by us. So now, with the nuclear world, we have a whole new vocabulary to introduce. Our nuclear terminology includes cross-section, how easy it is to cause a nucleus to react with another particle, decay type, alpha, beta, or gamma, half-life. Radioactive nuclei now have lives because they change on their own. And isotope, which means same place, and names different varieties of the same element. Isotopes are in the same place on the periodic table, but they aren't exactly the same substance. For example, the uranium that we mine here on Earth is actually a combination of two different kinds of uranium, called uranium-235, or U-235, and uranium-238, U-238, which are chemically indistinct, and they're both called uranium by a normal chemist. Those isotope numbers, 235 and 238, are the total number of protons and neutrons in the nucleus combined. All uranium has 92 protons, which is what makes it uranium, just like having 8 protons would make it oxygen. Uranium-235 has 143 neutrons, along with those 92 protons, making a total of 235, which is why it's called uranium-235. U-238 has 3 more. It has 146 neutrons, which, with the 92 protons, totals 238. This difference of 3 neutrons between 143 and 146 doesn't seem to mean much chemically, unlike a difference in protons, which would make a different chemical element. A different number of neutrons makes a different nuclear isotope. But there is a major difference here. Uranium-235 is fissile, meaning it will fission apart, split apart, when struck by a neutron, and uranium-238 is not. That's why uranium enrichment is performed, to concentrate the uranium-235 needed for a power plant. We still don't know why some isotopes undergo fission and others don't, or what the configuration or shape or nature of the nucleus is with these different numbers of nucleons. Examples of nuclear machines today include nuclear power plants, nuclear explosive devices, which, fine-tuned, could see application in excavation projects, medical scans that use special isotopes, or food irradiation to prevent disease and food waste and starvation from food spoilage. The power of a rock of uranium can do much, much more than a physical rock might weigh down on a lever, or a chemical rock, coal, might be burned to produce heat, although you can burn uranium if you want to. But this nuclear uranium can undergo a nuclear change and release 1,000,000 times more power than if you burned it chemically, and 1,000,000,000,000 times more than if it were used physically as a weight to push down on a grandfather clock to keep it running, for example. And that's only the part of its use that can be compared to lower levels of power, like making electricity or weighing things down. I mean, you can't perform a medical scan of your thyroid gland or look at broken bones in your arm with any number of rocks connected to pulleys, levers, corkscrews, or with a gigantic pile of charcoal, or with a bunch of chemicals. It's just a different kind of process. But today's nuclear is not the end of the story. We need to look ahead to fusion. Fusion is the necessary technology and power platform of the future. Unlike fission, which is the breaking apart of large nuclei, like uranium, fusion is the combining or joining, or fusing, of small nuclei. One example fusion reaction, the one that's most commonly studied today, is that between deuterium and tritium. Deuterium is an isotope of hydrogen, and all hydrogen nuclei have 1 proton, shown here in red. However, unlike most hydrogen, it also has a neutron, which we see here in blue. Since deuterium has 2 nucleons, it has the name deuterium from deutero, which means 2, like in duo or duet. Both normal hydrogen or deuterium, can form water by combining with oxygen. They're chemically nearly identical. Tritium, like tricycle, which has 3 wheels, is also a kind of hydrogen. It's an isotope of hydrogen, and it has a total of 3 nucleons, 1 proton, because it's hydrogen, and 2 neutrons, making a total of 3. Tritium. When deuterium and tritium combine nuclearly, which is difficult to make happen, and we still don't fully understand the process, there are a total of 2 protons and 3 neutrons, which results in a helium nucleus, 2 protons and 2 neutrons, and 1 extra neutron. Let's watch that again and count the nucleons. This is a nuclear characteristic. The chemical combination of 2 hydrogen atoms, including deuterium or tritium, just makes hydrogen gas and a tiny bit of heat. But the nuclear fusion can produce a huge amount of power, 1,000,000 times more. The magnitude of power made possible by fusion could eliminate the problem of droughts by large-scale desalination. It will eliminate resource shortages by making ore processing tremendously easier, allowing even low-quality mineral deposits to be mined. And it holds the potential to eliminate any shortages of power for living, commerce, industry, or agriculture. Plus, the fuel's easy to come by. Deuterium can be found in normal water, and tritium can be created from easy-to-find materials. But there is a problem with this planned deuterium-tritium fusion. Similar to the way you can't use a magnet to pick up a piece of plastic or paper, the neutrons made by deuterium-tritium fusion, those blue neutrons can't be controlled by a magnetic or electric field like those used in most fusion experiments. Here you see protons and neutrons, and only the protons are affected by the magnetic field. Since the neutrons cannot be directed, they just shoot off uncontrollably in whatever direction, and they hit the walls of the fusion device, making it get hot. Now, and this is embarrassing for these fusion scientists, but the current embarrassing plans for fusion power call for using that heat to boil water or heat a gas to spin a turbine, just like the steam power plants of the 1800s. A much more powerful and useful reaction is between helium-3 and deuterium. Helium-3 has 2 protons, which makes it helium, and unlike normal helium, which is helium-4, this helium-3 has only 1 neutron rather than 2. So 2 protons and 1 neutron, helium-3. Let's look at a fusion between helium-3 and deuterium. If we count up our nucleons, we see that combining helium-3 with deuterium gives a total of 3 protons and 2 neutrons, producing helium-4, 2 protons, 2 neutrons, and an extra proton. Unlike the uncontrollable neutrons we saw earlier, these products are both charged, allowing something very special to take place. The entire reaction, including the products, can be controlled by magnetism and electric fields, allowing us to go beyond the benefits of deuterium-tritium fusion. We could divert the products to directly make electricity without spinning turbines or heating anything. We could create proton beams for transmutation. We could use it to create directed space rocket fusion thrust, which we will need to have an adequate defense against asteroids, and many other properties that we have yet to discover. Helium-3 will allow us to finally stop using heat, a physical property, for power, and to truly work on the nuclear and electrical level. And acquiring helium-3 requires making a very big leap. one beyond our planet, in fact. There's very little helium-3 here on Earth, maybe a couple 100 pounds. But there are millions of tons on the Moon. China has expressed its intention to develop this resource, and the world should join this outlook. To review, we've discussed different levels of activity and understanding: physical, chemical, nuclear, and fusion. The tables you see show some of the language used for each level of understanding, which shows up in the questions of what is matter made of? What changes can we create? What technologies are at our disposal? We've seen that as we move smaller on the scale of our action, from physical stone tools to chemical reactions to tiny nuclear changes, we've moved much larger on the scale of our power, from physical machines based on motion to chemical ones based on combustion and transforming materials, to nuclear ones of incredible power and new capabilities. And in this nuclear world, 1 trillion times more powerfully, energetically, we've seen why it's helium-3 fusion, which will be the first kind of fire not based on heat, as we move more fully beyond the world of physical characteristics. Fusion is not an option. It is not a power source, and it must not be delayed. It is the natural next stage of human evolution, and is being pursued by leading BRICS nations, Brazil, Russia, India, China, and South Africa, even while it's being shut down and starved of funding in the US. If we are to join the new economic and political paradigm now blossoming around the world, we must embrace the creative identity of man and make fusion, with moon-based fuel, a goal that we are unwilling to postpone, one we intend to win.
Yeah, that was kind of silly, wasn't it? So for the next, I was going to talk about this, but I think we'll just read parts of it together. I'll say a little bit first, and we can read through some of it. This is a paper by Vernadsky that he wrote in 1930. So a little bit about Vernadsky. Vernadsky was a Russian-Ukrainian scientist. He got his start looking into soil science and geology, and realized that if you were going to be a geologist, you also have to be a biologist, and you have to study humanity. Because if you're looking through you're digging, you're looking through layers of rock, you find, different, we're in this era, we're in that era, it's the Cambrian, whatever. You find fossils in the rock. You also find minerals that only exist when there's life. They're photosynthesizing life. For example, granite couldn't be made if there hadn't been life on the planet. Not because living things make granite. Like coral, that's a living thing. Okay, that's directly made by living things. Nothing makes, oysters don't produce granite, But granite is a rock that has a higher chemical energy in it than could have existed without the extra oxygen and the energy made by life. So part of the energy available because of photosynthesis and the oxygen that was created made it possible to have granite. So if you're a geologist, you say, okay, I have to be a biogeologist, otherwise I don't understand these rocks. Obviously, if you find a shell, that was not made by a volcano or by erosion. It was made by a living thing that had a shell. And if you find a canal, or if you find a well, maybe you'd talk to an anthropologist, because that was made by a person, or a fire pit, that kind of thing. So overall, there's you just really can't look at any one field of science outside of looking at everything. And as Vernadsky stresses, everything has to include people. So he says he's disappointed that science has so separated out the world that the scientist investigates and the person who's doing the investigating. And it's so separated that the people doing the investigating are left out when you talk about what's the world made out of, what's the universal theory of everything. There are no people in that theory. There's no thought in that theory. There's not even life in that theory. So it's not a very universal theory if it leaves out the people who are developing it, right? So that might be enough to say start, and then it's going to be a little bit tough to pick exactly which parts of this to read. Let's read the first few pages, the whole of them. Do that. So the study of life and the new physics. How is the study of life going to change physics? Is that big enough? Should be bigger?
That's okay.
Okay. Any spirited reader like to volunteer for the first part?
I can do it.
Please.
The revolution which in our 20th century is taking place in physics raises for scientific thought the necessity of a new revision of fundamental biological representations. It seems that it is for the first time that it is becoming possible in the cosmos constructed by science to promote the phenomena of life to an important place. It is for the first time in the course of 3 centuries that the possibility of overcoming the profound contradictions created by the historic progress of thought is opening to us. Those which exist between the scientifically constructed cosmos and the life of humanity, between the conception of the surrounding world connected with the conscience of man and its scientific expression. This contradiction has penetrated our intellectual life since the 16th century. We feel it profoundly with each step. Its consequences are innumerable.
Make sure we get this. Just to make sure we get this profound contradiction. Right?
Mm-hmm.
The contradiction between the scientifically constructed cosmos, our understanding, our recreation of the universe based on how we think it works, and humanity. Between the conception of the surrounding world connected with the conscience of man and its scientific expression.
It is therefore important to follow attentively and to contemplate the development of the new physics as the changes produced in our life due to the creation of the new scientific picture of the cosmos. A consequence of the new physics in which the contradiction with the human sentiment will not exist. These changes grow with the progress of physics. This revolution must have no less of an impact upon the essential instrument of scientific thought, everyday scientific work, the psychology of researchers. Because it has created, as we will see, a striking unconformity in the course of recent centuries between the scientific picture of the world and the scientific work upon which it is based.
Is that too far?
A little bit. You can use the 2 fingers.
Is that the next?
Thus, we are witnessing one of the greatest processes in the progress of scientific thought, and one of the age-old crisis of human consciousness. Our scientific picture of the cosmos has its genesis at the time of the Renaissance. In the 16th century, Giordano Bruno, 1548 to 1600, clearly expressed the infinity of the universe and the small place occupied by our sun, not to mention the earth. Nicholas of Cusa, 1401 to 64, had understood this and expressed it 1 century before him. Bruno said with greater clarity than others, something which in that time was raised in all areas of human consciousness. In fact, the construction of Bruno was not a scientific acquisition, but he drew unprecedented philosophical conclusions from new scientific discoveries, conclusions which surpassed that which was scientifically known, and which was in agreement with the later development of scientific understanding. The entire scientific conception of the universe changed in a radical way. The tradition of thousands of years was shattered. The philosophical constructions deduced from new facts and scientific empirical generalizations got ahead of the later acquisitions of precise scientific thought by several generations. Based upon the telescope, a new conception, a new scientific sense of the universe developed in the course of a small number of generations. In the course of several decades, Copernicus, Kepler, Galileo, and Newton shattered the age-old relationship that had been formed between man and the universe. The scientific picture of the universe, embraced by the laws of Newton, left no room for any manifestations of life, although it appeared to have reached the limits of scientific perfection. Not only man, not only man, not only life, but our entire planet gets lost in the infinity of the cosmos. Up to now, man and through him, the phenomena of life occupied a central place in the cosmos, in the scientific, philosophical, religious, and artistic constructions. At the end of the 17th century, all of these representations disappeared from the scientific concepts about the universe. Ascribing excessive dimensions to the world, the new scientific concept of the universe seemed, at the same time, to belittle man with his interests and conquests, to belittle all the phenomena of life, to the point of being a species of insignificant detail in the cosmos. It seemed that the more human thought developed, the more such a scientifically constructed cosmos, totally foreign and inconceivable to all that lived, to every human personality and human life, came forward with more vigor and clarity. After Newton, this picture of the universe, devoid of life, penetrated by scientific thought, more quickly established itself outside of any philosophical or religious representations, due to the scientific observation of surrounding nature. The first of these epochs came at the end of the 18th century, the beginning of the 19th century, and the time of William Herschel and his sister Caroline Herschel, who discovered a new world and demonstrated for the first time the regularity of its construction. In particular, the existence of an infinite number of nebulae, of stellar cosmic systems. We are now living through the second epoch, in the 20th century. The new blossoming of stellar astronomy is in large part due, on the one hand, to powerful new methods of observation developed with an unprecedented momentum by the American observatories, and on the other hand, to the immediate adoption of scientific observations by physics. The new astrophysical discoveries penetrate the new physics and are more and more guided by its constructions.
Is this working? What can anybody restate anything that we just read, or any thoughts about this? This might be kind of tough to do this way. Any?
From the Renaissance.
What's he saying?
I'm saying that beginning with the Renaissance, you have this concept of life being the center of scientific thought, and that included in art, scientific thought, philosophy, and then after the Renaissance, you had this post-Renaissance period which was devoid of life.
Yeah, but he also attached the Renaissance to, well, certainly, you know, if you go back to Greece or whatever, the idea of man is the measure of things, this was just common. He's saying everyone took that sort of as a starting point. What are we like? That's the beginning to look at what's the universe like. and that with, he cites Newton in particular, with this change in science, that's now out. After Newton, this new picture of the universe, devoid of life, penetrated by scientific thought, it more quickly established itself, etc. Wait, there's a sentence before that was better. Yeah, that's the one. All right. The scientific picture of the universe, embraced by the laws of Newton, left no room for any manifestations of life, although it did appear to have reached the limits of scientific perfection. So, people sometimes say, well, Copernicus, he took us out of the center of the universe, right? He made us a speck. The Earth's a little tiny speck going around the sun. Later astronomy has shown how small the solar system is. We're just nothing almost. Physically, we get a lot smaller. And the ability to try to think that the universe must have something to do with us, or some relationship to us and connection, has been, really weakened by this development. And he says a little later, I just wanted to jump ahead a couple sections, he says that, people look to outside of science to try to move forward on this. We couldn't resolve the contradictions between our conception of the world, a human conception, and the scientific picture. The only way to resolve that had been through philosophy or religion. If you tried to stay true to science, you had to accept the scientific picture of the cosmos, which was formed to life. And we had to treat as an error and an illusion the importance which we always gave in life to intelligence and consciousness, to all living things of which we ourselves were a part. If you wanted to be a scientist, you had to do that. And yes, that everything must occur by the laws of science, so if we can't explain ourselves that way, maybe we don't exist. Faced with the impossibility of actually scientifically reducing phenomena of life into physical chemical processes, taking as a basis the picture of the cosmos of recent times, he brought about a great movement in the scientific environment and that of educated men, which proclaimed that sooner or later it would be done, without radically changing the founding principles, which were considered as unshakable. There's a faith that sooner or later will explain life from the scientific picture, without having to change the basis of this scientific picture. Newton thing, Bilas talks about. There's a part a little ahead that I really want to get into, so we're not just going to go through the whole thing with this kind of skimmy way, don't worry. Talks about the importance that Newton had, yet that so much of the new science that was developing wasn't based on Newton or on Laplace. He said, we're at a turning point. It's possible that the unconscious progress of scientific thought of the last decades has moved in a direction which has destroyed the belief in the possibility of reducing the phenomena of life to the parameters of the cosmos of Newton. Developments in biology making people less and less believe as a matter of faith that everything must be explainable from the Newton standpoint. Another quote, I had a little bit, and then discuss some of this. Here we go. Section 6. Oh, and this paper is originally written in French, too, so none of you can read the original, too, if you'd like to. Doubts are raised among naturalists. Naturalists mean scientists, which prevents them from admitting the primacy of mathematical, astronomical, and physical chemical sciences, this primacy which is inspired by the modern edifice, two conclusions must inevitably give rise to the doubts of the empirical naturalist. What are these two? Here they are. Cannot the life sciences effectively change the fundamental representations of the scientific universe, the representations of space, time, energy, matter, in a radical way? And is this list of fundamental elements of our scientific thought complete? Let's hear that again. Someone read that paragraph again? Sure.
Cannot the life sciences effectively change the fundamental representations of the scientific universe? The representations of space, time, energy, matter in a radical way? And is this list of fundamental elements of our scientific thought complete?
Think back to earlier about sometimes you ask the question that can't be answered in the language, like what's the density of carbon, for example. Is it possible that to try to explain life in terms, in these terms, space, time, energy, matter, is there something about those words and what they mean that will make it impossible to try to describe life in those terms as they are? Is it not possible that studying life might change those concepts? And is this list complete? Is there another fundamental concept that applies only in life that we simply wouldn't find outside of it? Like the word isotope comes up in nuclear science and not in the Stone Age. Is there another word that we ought to be adding, like isotope, that will make sense in the biological world, even if we don't see it in the non-living one? And then we'll look at some examples of how this has happened. Okay. This one.
Space, time, matter, and energy are clearly distinguished for the naturalist of the year 1929 from the space, time, matter, and energy of the naturalist of the 1900s.
This thing already has happened. In the past 3 decades, already, space, time, matter, and energy, these terms, they're just different. They may use the same word, but they're clearly distinguished in their meaning for a scientist in 1929 compared to what a scientist in 1900 would have meant. All of those words are different. Let's take each one of them. Space. Well, there's no Einstein in general relativity in 1900. There is by 1929. Time. Same thing. Well, it's one of the same thing. Matter. Also Einstein. Matter and energy used to be considered totally distinct. Conservation of matter, conservation of energy. Not anymore. Energy itself, Planck in 1900, and the quantization of energy. So, like, what would have been meant by any of those things is just the words themselves have already changed in the past 3 decades, as Vernadsky's writing this. So to say, why could life not, cause us to do this again? We're already changing what the words mean.
Even the concept of life itself probably changes in 30 years with more discoveries you make about life. That also makes you realize that these parameters are just too conservative.
So it's like Vernadsky saying that we're kind of like holding ourselves back by not looking at science through a life, like a subjective lens as well, whether we're just looking at it through as objective as possible, and these are the laws, this is exactly what it is, no life involved, just this is what it has to be. So is he like trying to say that we hold ourselves back, that we could probably like make a greater leap much more faster and much more like, progressive, I guess, if we also used our life within it? Because I read the rest of the paper and it was very confusing, but I kind of got like some stuff with it.
Yeah, he would definitely say we're holding ourselves back. He wouldn't, the terms he uses aren't, he wouldn't use the term or he doesn't use the terms subjective and objective. He distinguishes between abiotic and living and the thought. Right? So he'd say by not allowing there to be specifically biological principles, we're holding ourselves back. Because then we're saying, if we're trying, whatever we might, find in biology, we got to explain it in the chemistry department. And he's saying, well, what if there are things that are just in the biology department? Just like the nuclear department has the word isotope, and the old chemistry department didn't. So are we holding ourselves back by trying to explain everything with too low a level of the language? So what this whole paper is about is how can we change physics, do it the other way. How is physics going to change by studying life? You know, he does say that, you know, and he considers himself, you know, he says that he doesn't like to make hypotheses. Well, he does. He makes empirical generalizations. So he does not have a lot of respect for how people would use philosophy in a kind of an abstract way to say things about physics or life or anything like that. He says you should base it on, you know, actual observations that you make, but feel free to make them. Like his whole approach is like looking at human beings as a geological force. Like, okay, well, what moves more matter these days, mining or volcanoes? Nowadays, mining. So, you know, just look at, you know, what is the human species like? It's a species that, unlike others, changes its carrying capacity. That's not a philosophical, that's just, he says, that's just an empirical generalization. That's what's happened over the history of mankind. So what does that mean about mankind? So he gives a couple of examples of things that are specific about, and there's specific ways that he knew about already that all of these could change again with life.
I have a question, Jason.
Yeah.
How is that different than the Aristotle thing?
Oh, say?
You said Vernadsky used the empirical generalizations. This is what we've seen happen. How is that different than the way that Aristotle did it?
Well, the other thing Aristotle did was to say that not only do we get all of our knowledge from the senses, but in large part he already had it all figured out too. So, that's a good question. I don't know why Vernadsky uses language that way, because he's in a context too. Like what he's trying to do is he's trying to say that there are insights about the nature of mankind that are useful and valid, and they're not going to come from philosophy itself. They're going to come from like investigating. In other words, he's got like a whole new way of investigating what is the human species and what is life. So
I think Vernadsky does have certain fundamental hypotheses. Like the biosphere, he does not merely begin by building up a discussion of what we've observed on the Earth. He begins with a hypothesis that the Earth is part of the cosmos. Anyway, I was reading some of the stuff that one of his teachers, Mendeleev, wrote. You do have a certain hypothesis on where the universe comes from. And so I think I do think Vernadsky is very emphatic on the question of honestly looking at the empirics, but he also has a worldview.
he does, yeah. Yeah. He's not going to say something without some. In other words, he'll like actually.
He doesn't like change the data to try to support his own opinion, but he does have opinions.
Yeah, I agree. Just about the space. We're going to come right back to space, time, matter, and energy.
Isn't he saying that that same thing, like space, time, matter, energy, are also defined, because the mainstream science or particle science today try to put particle or matter as source of everything, but it does not, define how life is created or how consciousness is created, use consciousness to be out of it.
Mm-hmm.
So is that what it is? Just to be able to those same things to be also be able to define consciousness or life, or if not, that evolve it. That's what it does.
Yeah, they definitely. The fact that those things exist mean that you have to then acknowledge they exist. Sort of cut a little bit more here. So he's not going to dwell on everything. He says, so what's essential is the complete change in our notions of space, time, energy, gravitation, and matter. The force of universal gravitation, acting instantaneously upon every considerable distance, disappeared without a trace from our thoughts. Gravitation doesn't exist anymore with general relativity in the way that it used to. Space and time are inseparable, and to understand physical phenomena, we're forced to employ geometrically space of not 3, but 4 dimensions, including time. The boundary separating energy from matter fades. E equals mc squared. Energy is propagated in strictly determined jumps, quantum. The physicists still thought at the beginning of this century much differently than we do today. I remember a conversation I had more than 20 years ago with P.N. Lebedev, the eminent physicist, who told me that he was only secure speaking about the ether. This was at the time that the notion of the electron just began to enter into physics. Currently, physicists try not to speak of the ether, and there are those who doubt its very existence.
The ether is the soul or something?
The ether was the hypothesized substance that light moves through, because light, Newton said that light was like little balls sort of flying out.
Particle wave theory.
Well, yeah, Newton was a particle theory, and then Huygens had a wave theory of light. And so people say, well, how do you explain both of them? I mean, the fact that light can. Does anyone have a laser? Is there a laser pointer here? Do you know one? If we get one, we can even see that. You can actually just do it with a pen and a laser. If we find it, we can actually see the waves. So light does things where it acts like waves, and so it seemed like how does that work? If it's a wave of what? So the ether was the stuff that light moved through like a wave. So the ether was how you explain what it is that light moves through. Because if there's this experiment, I think Huygens did it. He took a big jar and he put it over a clock, and he attached a vacuum pump to it. And as he sucked the air out, the tick-tock of the clock, you couldn't hear it anymore, because you need air for the sound to move through. But you could still see the clock. So he's like, well, what's the light? We took everything out of there. Is there still? So maybe there's ether is like flowing through the glass, because it's so thin that it can go through everything. So it was kind of, it was a medium that light moved through. That's what the ether was.
So has ether been observed physically or chemically or whatever?
Well, the test to do it was the big one was the Michelson-Morley experiment, which is where it was like a cross-shaped device where you would put. So let's say basically it was based on the idea that the Earth is moving very rapidly, at least compared to the Sun. If the Earth is moving, it must be moving through the ether in some direction. If overall the ether is sitting still and we're going right through it, maybe we can determine what direction we're moving through the ether. So to do the experiment, they tried to say that if you're in a river, there's a river flowing this way. If you swim across the river and back, it would take a certain amount of time. And the fact that the river is flowing this way isn't really going to have much of an effect on you. Versus if you swim up the river and then back, that same distance.
Will this work? Kind of, right?
See it?
Kind of tiny.
Let's try it in a little bit. It might work. Yeah, that, and then just if there's like a sharp pin or earrings work fine too. If this one's
Yeah, it does.
So I'm forgetting which one. I think this one ends up taking a little bit longer. Like in other words, if you're swimming and you wanted to come back here, you have to act like you're actually swimming upstream because the current's also putting you back. So you end up actually having to sort of swim like this, and you'll still wind up back where you were. And then if you're going up the river against the current and then with it, it's like you had to swim actually up this far because the current pushes you back down. And then when you come back, you only really have to swim that far because the current actually pushed you part of the way. And so the total distance of swimming this way versus this total distance of swimming, I think this one's a little bit longer than the other one. So by timing how long it took to swim, either against the river this way, perpendicular to the current or in the direction of the current, the times would be different. What the experiment did was it shot two beams of light. One beam of light went this way, bounced off a mirror and came back. The other beam of light went this way, bounced off a mirror and came back. So by reorienting the device, you'd be able to figure out, it's sort of like if you had this thing in the river of the ether, when the device was oriented, so one was going, in the direction against the current, and the other was perpendicular to the current, the light swimmer should take a different amount of time going this way versus this way. And the way they try to look for the difference in time was to use it uses the wave nature of light. That you couldn't measure time that accurately. I mean, it's so quick. So basically what they do is they do it by counting the number of wavelengths. This light's going up like this, and it bounces and it comes back. You can see, well, when it comes back, is it like at the top, is it at the bottom of its wave? And the same thing with the light going this way. And you'd compare whether they're both at the top or both at the bottom. That's the way that it's called interferometry, a way of measuring distance by a difference in the phase angle, where it is in its wave, is a way of. We actually have satellites that use that technique to measure how the Earth's shape is changing. They use light to watch the Earth, and they do it not by timing it like radar, but shooting the light down and then seeing what part of the wave it's at when it comes back. Anyway, so this experiment was done to try to figure out, which way is the ether pointing, which way is the Earth moving through the ether, and they didn't find anything.
If so using this logic, ether wouldn't necessarily exist, let's say, in water, because the deeper you go in water, the less light, and there's a nuclear reactor that's submerged in water that gives off the radiation gives off a blue light that moves faster than natural as well. So I don't know. It seems like off odd, how ether can't really.
Yeah, it gets kind of weird because then there's ether, but also obviously the fact they're going through water or or just a colored like sunglasses. Like if it was just going through the ether, why did it get darker when it went through your sunglasses? So it wasn't the whole theory. It was, but they had to have something for it to go through when you took away everything else. So. It was in I think the first decade of the 1900s, early 1900s. And so, the way it seemed to come out was that they couldn't, it didn't seem to make any difference, whichever way you pointed it. So, maybe there's no ether. Although other people explained it differently, that there still was an ether, and just that the ether got kind of squished when you went, in the direction of it, and it was looser than the others. So, if you still wanted to believe in the ether, you could, even with that experiment. So, Lorentz. You may have heard the formulas, the Lorentz contractions. They're how general special relativity gets applied. He believed in the ether, and he came up with those equations to be able to accept that while still having an ether. Maybe that's too much. Okay. Anyway. So Vernadskys, okay, 20 years ago, this physicist friend of his talked about the ether, and now physicists try not to speak of the ether. Now he wouldn't mention it at a party. Big difference in just a couple of decades. Then he talks about life. When he gets this thing about time, a few paragraphs ahead. Oh, and then atoms, right? People didn't like atoms, but now everyone, no, you'd be embarrassed to say you didn't believe in atoms. Yeah, right. That also happened over just a few decades. Okay, here's another one. Right, so there had not been room there, in Newton's, there had not been room for irreversible processes in physico-chemical phenomena embraced by scientific theory in the Newtonian universe, which has reigned at the beginning of this century. All natural processes in that context were always considered de facto
as reversible. This principle constitutes the basis of the scientific representation of a cosmos of the 19th century. In the case, and I know reversible and irreversible might not mean something yet, so just one more sentence. In the case where they seem to be irreversible, only an apparent irreversibility was assumed, and some scientists accepted the idea of a very slow development, to the point of being absurd, of a reversible process. Today, the irreversible process plays another role in physics, probably an important one. So reversible and irreversible. All of the laws of dynamics, all of the laws of motion, like Newton or whatever, are called reversible, meaning that if you made something move in the opposite direction, the laws won't change. It's kind of like relativity. It goes to Leibniz. So, you know, however the laws of physics are this way, if I'm walking this way, they, none of them change. And not only for direction in space, but direction in time. So whatever laws of physics describe moving forward in time, they all look just the same for moving backward in time. It comes up that any formula that you write, if you switch the time from plus to minus, you don't change the formula. How should I describe that? Like, in other words, like the planets are all going around the sun. If they're all going the other way around the sun, I wouldn't violate anything. Gravitation's a reversible phenomenon. The irreversibility came up in thermodynamics, where people,
Like ice?
Yeah, like mixing temperatures. Or, it's like, well, you know what? Heat doesn't flow from a cold body to a hot body. It doesn't make, if you put ice in water, in warm water, the ice is going to get warmer and the water is going to get colder. If you looked at it on like each atom and what it's doing, it would be possible for the ice to get colder and the water to get warmer. That doesn't violate the conservation of energy. Or if you thermodynamics is weird. So anyway, but like in the study of heat, things weren't reversible. You couldn't go backwards. A heat engine is never 100% efficient, for example. So the heat that you put into a steam engine, or the heat that's in your car engine or whatever, after it does what it does, it creates some motion, and there's just some residual warmth that's not very hot. You're never going to be able to go back and get all that heat back again. You'll never, not having 100% efficiency is another form of this irreversible thing. And so it shows up in things like the idea of entropy, that over time disorder increases, that energy gets to less and less useful forms. So I've got like some nice motion, it's a nice directed kind of energy. If I'm dragging this along the table, I'm losing part of it in the friction, which just makes this get a little bit hot. That's a lower form of energy. So anyway, heat flow is considered irreversible. And all the laws of motion and dynamics and all that are reversible. That's another aspect about how time had changed in the past few decades. So space-time, energy, and matter. Let's take a look at life now. And I don't think we're gonna. I just didn't pick out more specific parts to read, but to say something about it. Start with actually. Could you grab the two orange things out of the back? The plasticky things.
Okay, it'll be up here.
Apparent?
It'll be obvious what you're talking about.
Oh yeah, they're like made out of like plasticky. They're zones things.
Okay.
Yeah. Okay, so back to that thing about handedness. So are there any? I feel like I might be going. Are there any questions?
I had one. I was just wondering, this paper was written, when did, for the first time, Vernadsky mentioned the Nöosphere?
Later.
Okay. Later. Okay.
Yeah, I think. I have a very bad sense of time.
and for Vernadsky it's extra bad. So. He doesn't say it in this paper anywhere. He doesn't use the word, that's for sure. So, okay, so here's one example about the time thing. So over evolutionary time, it's like, here's a couple other kinds of time in life. Generations. Right. Rocks don't have generations. There's not generations of friction. By generations, I mean like, parents and kids, that kind of, right. Friction doesn't like get older and then like there's a new kind of friction and then it gets old and then something else starts again. None of that really happens. But in life, you've got generations, you've got evolution. Those are two kinds of time that don't exist for non-living things. You've got the fact that the time of life, not only does it have a direction, but the after time is different than the before time.
And it's irreversible.
It's irreversible, but it's irreversible in a bigger way than thermodynamics. So if I mix cold and hot water, it'll just sort of mix and become warm, and that's considered irreversible. The water is very unlikely, even though if you look at every atom of that water, it's not impossible for it to wind up that half of your cup of water is really cold and the other half's boiling. It could happen. It doesn't. It only goes in that one way. It's considered irreversible. With life, it's not that cold and hot mix and get warm, and it's irreversible. It's that you've got, cold and hot then become...
It's not random.
Well, it's that you reach a stage that you couldn't have even had before. It's like, oh, we've now got warm-blooded creatures. Or, oh, life moved out of the oceans and is now on land. So it's a different kind of irreversibility, where it's not just a different state among the ones that might have already existed, you've actually created a whole new level. And so he's got these two principles of biology, two biogeochemical principles. One is that life tries to maximize the energy in life. And the other one is that over evolution, it's those forms of life that do that the best. Those are the ones that will exist over evolutionary time.
Maximize the energy as if you produce maximum or consume?
The overall flow of energy. So he thought, for example, that the mass of life hadn't changed in 1 billion years. I don't know how he thought that when life didn't exist on land 1 billion years ago, but whatever, he thought that. But he said the energy is increasing. Life's getting more energetic. So you see it with like reptiles versus mammals, for example. Reptiles use way less energy than mammals do. But what survived evolution? Well, we're both here now, but but if you just did it based on reptiles use less energy, you'd expect there wouldn't be any mammals, but there are, right? The predominance of mammals is great now compared to when mammals first existed. We took over. Plants that have seeds, they took over. If you go around like, okay, how many ferns are there versus how many trees and bushes and things like that are there? Ferns don't have seeds. They're an earlier form of life. It's like they didn't really... Ferns are almost like they're still living in the water, because when ferns reproduce, they make male and female parts that have to go and mix out in the wild, whereas plants with seeds, the pollination occurs in the plant. Right. So like a flowering plant or whatever, from the stamen over here and the pistil and all that, and then it's pollinated inside. Or like life, like mammals, reproduction occurs inside, whereas fish, just male and female fish just squirt things out and then they mix in the water. It's not internal. So ferns are like that old tradition, where they do the sexual part of their reproduction occurs outside in the environment. And more modern plants, it's internal. Anyway, it's like, so these things are increasing. So evolution, he's like, it's not just sort of whatever happens to live better. There's a direction overall that life is more energetic. So he's got those are some of the things about, were those things there? I might have taken them out. Yeah, that's it. Okay. Is there another? What? I think there's another.
Another tiny one that broke off.
It should be 2 yellows and 2 whites. I think are still.
2 yellows and
Yeah.
2 blacks and 2 whites?
No, I mean no. 2. It'll look like just that.
Oh, I see.
Together. Anyway, it's just a little bit about time, how time's different with life. Now we can look at how space is different in life. You know what? It's okay, I don't even need that thing. Oh, no, I'm good. This is a chiral, right. Okay. So these are like hands.
Mm-hmm.
They're the same, but they're mirror images of each other. They're not exactly the same. You see with the little feet. One's black and one's white. So I can say these aren't, in one respect they're the same, but they're also not. If I had only, if I did this, if I gave you one of these, and I gave Courtney one of these, can you, without seeing them, can you describe them, or can anyone think of ways of describing them to each other, where you can figure out, are they the same or not? I don't know if that's a clear question. Like, we saw them, we held them together, and we said, no, they're not the same. They're mirror images of each other. But if you only see one at a time and use words and describe it and talk about it, can you figure them out?
Yes, you can visualize.
So you want me to tell Courtney?
Or anybody. Is there? Can anybody think of any way of just saying?
Say it's yours, but just your black pieces on the opposite side.
Oh, but you haven't seen the other one.
Yeah.
Okay.
Let's just say, like, is there some way of describing this?
Well, let's see.
What if you put it like set it down? Because if you're holding it and moving it, there's no way you'll ever be able to describe it the same. But if you put it down on an object at least where it has like a set
fixed
spot,
position.
you could at least say, hey, this is yours. Have like this thing branching out on top of it.
Yeah, you give it a view first, like the front view.
What's
What is the front?
yeah? Which
Well, by putting it on something.
yeah? What would be the? I'm gonna put it over here once we figure out what that view would be. What's How should it be placed?
Yeah, it's
Well, it
just
doesn't really matter actually.
Yeah, it doesn't
Yeah.
matter.
One thing you could say, it's funny. I don't know how they describe it in chemistry, but there's one axis along which
Yeah.
all of them lie, and then there's another
Okay.
axis,
Right.
Yeah.
and they're at 90 degrees to each other. So that's the first approximation.
That's the first. Okay, good.
Mhm.
So one thing to know whether they're the same or not, because maybe Courtney has a completely different shape. What could we say about this one and ask Courtney to verify it?
On the wall.
Cheerios.
Well, we could start with maybe what Frank said. Does Courtney, we're not looking. Does yours have like one main axis and then another one at 90 degrees to it?
Yes.
Okay.
Oh, so is mine.
How many? This is made up of how many balls are in this one?
8. Yes.
8. Okay.
And 7 middle connecting pieces, connecting rods.
Oh, 7 connecting rods. Okay.
Then you could maybe say set of 5 of which or 4 of which lie on that straight axis that we already established.
1, 2, 3, 7, 6.
Yeah.
6 lie on the same axis.
Can you split it into
Same?
symmetrical?
Could you like build it step by step? So you start from the beginning of your axis, the
Great idea.
first ball, and then say you have a connecting rod going 90 degrees to a second ball. Then you have another connecting rod going 90 degrees up to the next, and then so on and so forth.
Let's do the whole description. Let's see if they're any different. In fact, why don't we just hold both of them up here so we can see them both? Okay. And we'll see when the description. Is this too low? Should I hold them up? Okay, I'll hold them. So, okay, go ahead and start describing the way of making it, and we'll see when it doesn't describe both of them.
Okay, so you have your plane, so your x and y axis. Let's say the first ball will start on your origin, so 0, 0. And then continuing on, so the rod will be, I guess, connecting. The rod's connecting from, let's say, 0 to 2, and just on the x-axis, and then you continue, but it's a 3D object, so I don't know that the x, y, z.
Well, you could do this.
Yeah.
You could say, you could start with the first ball on any end, it doesn't matter. And you say that ball is connected to another one. That connection is obviously going to be a straight line. And then the next step is interesting because you have to define an angle. Let's say 120. It's slightly bigger than 90. So the angle. So you have the first 1 to 2 on both of them, first 2 balls, and then the third ball is connected to the second one at an angle of 120 degrees. And then the fourth ball is the same thing, 120 degrees in the opposite direction, and 120 degrees in the opposite direction, and 120 degrees in the opposite direction. And that's at least that one axis. So you explain that. And then you can say on the fourth or third ball, whatever end you want to start from,
Right, okay.
that's where I begin to build the other axis.
Good. So how do we make sure that we're able to describe that they're supposed to be different? We've got our third balls here, so third or fourth ball, whatever.
Maybe saying that, well, I think I'll make a distinction. It won't be balls. Let's say it'll be squares. And then you direct it. You give it a position on the axis, and each of the squares would be opposite to each other.
And perpendicular to the main axis.
Yeah,
Perpendicular.
Yeah.
Well, okay, so how do you tell me whether to put the white one over here or over here? How do I do that?
It's up to you.
It has to be perpendicular and.
Oh well, yeah, it has to be 90 degrees to the thing.
Okay. So I'm gonna do that. Now so then I gotta make this one different. So make sure you gotta make sure I don't do this one the same way. Or let's say you've got another person on the phone, and they say, "Oh, okay, yeah, I got you." Yeah. They're starting to make them. They're going to be the same. How would you tell? You get 2 different people. You're talking to them. How are you going to make them make the different opposite ones?
Well, you direct it. You say you just put one ball on whichever side you want, and
Which side?
okay, the right side, 90 degrees.
What's right?
Looking upon the x-axis. So.
Well, hold the thing in your left hand.
Okay.
With your right hand.
Now let's say you're talking to an alien by telephone, and they say right and left. I'm not quite sure what those words mean. Could you define them for me, please? Which one's right?
Oh, that's funny.
On the plane, right is positive. Right of the x-axis is positive, and then left is negative.
Oh, this is positive. So this one's positive?
I actually don't know.
Uh-oh.
Yeah.
Which plane?
What's a plane?
Well, we got
The axis,
these are
the
in a
axis.
plane.
Okay.
We're assuming that aliens have some sort of taxi.
Because some of the stuff we could just, because what happened before was add another one, 120 degrees, now go the opposite way, stay in the plane. Those were, I don't think that those were, maybe we just went over it too quick, but I think those were, I don't think those were ambiguous.
What if you had the axis? Yeah, I'm sorry. What if you had the axis like you look, but more towards, put it next to the board, the other way around, the way you were holding it. No, this side.
Okay.
And you say, well, so you have it on the plane, coming towards you or coming out of the plane. There's going to be whichever, like the white. Or
Okay, coming out of the plane will be the white
Coming
one.
out of
Sure.
the plane.
Which ball do I attach that to? Which one do I attach it?
The third.
The third one?
The thing, yeah.
The
what's
third counting from like this
Zero,
third or
zero.
this third? Do I start from the left or the right?
It's
yeah.
Or maybe I start from, maybe say the third start from the one that goes up.
Yeah.
Maybe that would work.
Which
Oh,
Maybe you
direction?
can just flip
I have a question. Which direction do we start building that first access in?
Ah, that'd be good.
it. Like I
That's-
said, the
That's your
origin.
that's your unit.
I think we
Direction.
started here,
Yeah.
and then we do. Now, I also don't know if we made it this way versus this way.
Yeah.
But maybe you could say to the alien, you're on a planet, move, in the direction gravity pulls things, and also to the side. So maybe that would work. I think we might have this orientation, okay. And then I put it against the board, right? Okay, so I'm gonna put it against the board. Wait, do I put it against? Do I put it against the board this way? Or I'm gonna take the third one, or the fourth one. I mean.
Does this
Which way, do I put it this way or this way? To have it pointing out of the board.
Does this alien idiot guy understand? We use the word perpendicular, right, already.
Yeah,
I think
that's
we
okay.
understood it.
Yeah.
Let's keep it in space. It seems to be easier if you keep it in space.
Okay.
You just let it float around. Or maybe it could be simpler. And you could say, because you did describe going from one ball to the next ball to the next ball to the next ball.
Right,
So you have a
yep.
sense of counting. And say on the fourth ball that we created.
1, 2, 3, 4. Okay.
We did the whole thing, so we
Right.
have all 6, but on the fourth
Right.
ball we created, I have to, because it's all the same material except for that black ball.
Right.
Because it's all the same atom except for the black ball.
Right.
So you can say I have everything the same except for one thing, just to put it out there. And and perpendicular to that fourth ball
Mm-hmm.
at a 120-degree angle, because we seem to understand that also,
Mhm.
pointing down,
Pointing down. Okay. Uh-huh.
I have a white ball to the.
Uh-oh.
So I guess we can find the physical process of.
But where do these words come? What are some other? Are there any other words we can use to say left versus right? Besides left and right, are there any processes that go one way versus the other, that point one way or another?
Pretty
Clocks. What determines clockwise?
Oh, yeah, the position in the circle.
Comes from a sundial.
Yep.
So in the northern hemisphere of the Earth, the shadow goes clockwise. If we invented clocks, if clocks were invented in the southern hemisphere, clockwise would be the other way. So that might be tough, because I don't know when we called this alien up, I don't know if we know which way their planet's spinning.
If they've ever visited Earth.
Have you ever visited Earth?
Oh.
No. Oh.
No. I got it.
Okay.
He understands degrees on a circle.
Sure.
We could use that for direction.
But which way again?
Let's try it.
Let's try it. Okay,
Let's
good.
try it.
Okay, good.
Let's try it.
Some degrees here.
From that same.
There's 2 90s.
But you said, what'd you say?
I'm an alien at a whiteboard here.
Oh,
ready
so,
for it.
so there's 120.
Yeah, 120. Yeah.
Yep.
That means,
And then there's 2. Then there's 240.
You can make a V and inverted V.
Say that again.
V and inverted V.
V and
Describe
negative
that.
V.
To describe what?
I mean, whether it like goes, whether the
Yeah, because
point
if
is
you
down
describe-
or up. 'Cause I put down and up. There's something meaningful. You say, well, you're on a planet. Down is towards the center of your planet.
Right.
I think they could distinguish between these two.
Yeah.
Yeah. Okay, so down and up. Got it. Absolutely, I agree.
But it was also a thing of direction, because you say, for instance, once you built the third ball, you had to have a sense of direction, i.e., rotation. Do they understand?
Wait, the direction. You mean when you go like this?
Yeah.
I just think you might have called them up and they might have been building it like this, or they might have been building it like this. I don't think you're really
Can you
gonna,
put
you
it
know.
in the direction of the setting of the sun or something? They're in the same spectrum.
What if they're not? What if they're not? What if we've never seen anything in common? We've still got the laws of physics are all the same. Let's say, oh, that's the same. You know, so gravity, down still means something. But
So wait, are we trying to replicate theirs, or are they trying to replicate like?
we're trying to call them up, and so basically we got the aliens on the phone, and we're saying, you know what, life on our planet is
This way?
is asymmetric. You know what? There's let's say we described, you know, we're like, you know what, when we make we call them up and we say, you know, we came up with this pill that really helped morning sickness, but it caused birth defects too. And we realized it's because there are two different mirror images of the molecules, and then you know, this is the one that works, the other one doesn't. And they say, oh great, we'd really like to know that because, man, you know, our alien ladies have really bad morning sickness. Could you please tell us which one to take? So we're on the phone and we're trying to describe to them this one and not that one. They're like, oh yeah, we've noticed the same thing. Yeah, they're definitely biological things, they're one or the other, and yeah, we've noticed that too. Life's like that for us.
So if they have one, can we just say the opposite, a mirror image?
Of what they have.
If they have their own existing version, let's say that, and we just say mirror, make a mirror image of that.
But how would
Well,
you
which
know
one's
if-
the first
yeah.
dad, I guess? Maybe I made it too
Well, it doesn't
specific
matter
with
if
the
there's a
birth
first or a second. If they have a completed version, that's all that matters, because then we just mirror that and.
What, I guess here's another one. What if and they say, oh yeah, that's so amazing. We use these things that are called proteins. Maybe they wouldn't say those. Use this, you know, we got zigzags and they're made of, you know, this thing that's shaped like a spiral in our cells, and then you know, it's got a code in it, and we make amino acids, we put them together, we make proteins, and then we say, hey, you know what? Our proteins are left-handed. They rotate light to the left, and they might say, oh, maybe ours do too. I'm not quite sure what you mean by left-handed. Is there any way to actually tell an alien left versus right-handed, or clockwise and counterclockwise? That's what we're trying to do right now. Like,
Would it help to start close and build far?
yeah, I think close and far that would work. I mean, I think that like at this point, like I think we can be certain that the aliens are sitting there like, okay, I've got this thing. It's going away from me. I first went down, and then I went up. Now I've got 6 of them, and you want me to put 2 things on the 4th ball. I'm with you.
Okay.
I just need to know, you told me to put a black one on one side and a white one on the other. Which side does the black one go on? Does it go on the blip side or the flip side? And you say, I don't know what those words mean. And they say, I don't really know how to, how would we like talk over the phone and figure out what we're doing?
Well, you I guess question each other on how yours looks like.
And say, yeah, our black one's on flip.
Maybe we could say that I'm raising my right hand, and then they say, well, I'm raising my flip hand, and then you're like, okay, so we've established these are both rights.
Oh, this isn't a Skype call. This is just on a telephone.
Maybe if you get him, if you get him to go, oh, like to make a long note while he moves the phone around, you can tell him, okay, that's the right side. That's the right side.
Would it be different?
You might hear it. You might be able to tell which way it's going. If you have earphones.
Okay, wait. Let's.
Okay, this is not a stereo phone call. This is an old-fashioned telephone. No Skype, no stereo.
They're on a planet that revolves around something. But
Yeah, you call it. They're like, yeah, our planet. Yeah, it spins. Yeah, it goes day and then night, day and night.
well, their rotation around the sun can be described as one direction, and then you say the opposite is. Let's say they're moving around it
Mhm.
left, and that's the way it is. And if you would just reverse that, and make it a right.
They'd say, oh yeah, totally, yeah. We go around in the blip direction, and we go around the sun that way, and we also spin in the blip direction. But in the southern hemisphere, it looks like it goes in the flip direction. But you know, whatever. I shouldn't have said southern. In the they're going to have words for all those things. I guess the question is, if we're trying to like work out like a translation dictionary or something, would we be, you know, unless we can send them a postcard, like someone waving their right hand, can we do it just by talking? or by the intrinsic characteristics of right and left. Because some of them like away from you and closer to you, that seems like
Well,
everyone
they-
should have a concept of that. And then down and up
down.
from, you know, you stand on the ground, okay?
Do they have the same biological like, laws that we have? Like if we put them, if we told them, all right, stand in anatomical position with your back, your posterior, or your dorsal end to a wall, okay?
Okay.
Any wall.
Sure.
So now you've created the axis of your own anatomical position, okay? And then you can tell them, raise the, I don't know, raise your flip-flop side, whatever. And then they said, okay, I have it raised, right? And now you tell them, okay, now, if you were to walk in that same direction, does your hand ever like, does your fist ever hit a wall, or will it like, you know?
Oh, you mean like if you're standing in a corner where it's like this?
Sort of,
like
yeah.
that? So I
you
have to
can
know
establish
what.
it. Yeah, like no, this hand did not hit a wall, but if I moved into the zip lap direction in my anatomical origin, I do hit the wall. So now you've established that they're moving in that direction. I mean, I don't know.
They'd say,
Well,
yeah,
if
if I'm
you
against
ask-
the flip-flop corner, my flip-flop hand goes out. And if I'm in the flip-flop corner, I can put my flip-flop hand out.
Can you ask them
Would you still know which corner they were standing in?
which side their heart is on?
Oh, yeah, it's on the flip-flop side.
But that is the right side then.
If
They might not
they're
have
made the
it.
same
Yeah,
way.
right.
They might not be
What if they said, which one? We have 5.
Oh my God.
No, but they might, maybe the heart's, who knows?
So what are you trying to like?
Oh yeah.
Well,
So
it's
we
really
can't-
hard,
we
that's
can't
one
just-
thing.
No, I'm just kidding.
That's what we call
Like,
the aliens.
based on
Hanging
gravity,
up on you.
you can like make a system of direction. I say if you drop an object and it goes that way, that means the opposite is up.
Yes, down, up, agree.
Yeah, so we can like down and up is easily like definable, but for left and right, like that's a problem.
It really is a
So-
big, it's a, huh?
Do we have the same definition of positive charges and negative charges?
Very good question. Well, you can describe them.
Positive charges are the nucleus of the atom, so we can mark that.
Good, yeah, keep going with that. That sounds good. Yeah, they'd say, yes, the nucleus of the atom. You call that positive? Oh, we called it yeah, sure, we'll call that positive. Okay.
Okay.
The electrons around it, we'll call them, they're negative. I agree with you, says the
Then
Which
let's say have a flow of positive charges from
Okay.
you and away.
Okay.
That will create a magnetic field.
Okay. How do I determine? I think you might be onto something because magnetism and electricity is a three-dimensional kind of force. So, okay, so I've got positive. I'm shooting, let's say, positive things away from me. So, what does that do with the?
So it creates a magnetic field like this.
Agree. Yes. It would make your magnetic field this way. We're using our language, right?
Yeah. So if you send another positive charge on top of that positive charge, the magnetic field, because the magnetic field is like this, so, and the flow of positive charge is like this, so the positive charge will be pushed to what we call left. Then we can get a definition.
The positive charge would be pushed towards the left. I just want to make sure we're not jumping to conclusions. So I've got a positive charge coming out of me,
Yeah.
which makes a magnetic field pointing this way.
Yeah.
Then I shoot another positive one above it.
Yeah.
This. So the charge is going this way. We would call the field going this way.
Yeah.
And then what's going to happen?
So we have the field like this. Is it positive?
I've got my QE,
Field.
right? And my charge going this way.
This field. Yeah. This is direction.
This is the magnetic field. So from the one below it,
Yeah.
so the magnetic field's pointing this way. I shoot another proton through the field. Which way is it pushed? Down.
Down.
Right. So it stayed in the plane, which we already knew what up and down were.
I have an idea.
I like that direction of thought.
Electrons have spin.
Okay.
That was high school, but electrons have spin left and right. So I don't.
We-
Depending on the,
yeah.
I think that can be used.
is there an experiment that has an absolute difference for electrons that spin one way versus another? This thing about the magnet, that's good. Here's the thing you might, the trouble is that the direction of the magnetic field itself
Yeah, that's defined
came
by
from
us.
a convention of the north and south poles of the Earth. So it came, it's a positive, negative, that's, yeah, that has absolute meaning for the nucleus and the electrons. But in terms of, we say the magnetic field goes this way,
Yeah.
but it said it went this way, and then use the left-hand rule. North and south is arbitrary. And maybe we can come up with a real, at least so far it looks like it's arbitrary.
This seems more like a difficult
It's tough.
in communication
Could you-
rather than
Even
like.
degrees are arbitrary. So like 260 is a number that we define because it's easily divisible by 2, 3,
Yeah,
4,
six,
6. So we choose like 360 as a number. It's
Right.
not like a circle can have 500 degrees if you want.
Well, however many degrees it has, does it have a direction when I say through? I mean, maybe I count the degrees this way, like a clock.
Could you?
Although in geometry class, they usually count them the other way.
Could you?
Right,
Could you say they know?
with the radian?
They know up and down.
They don't, yeah, gravity
So-
and opposite, yeah.
Could you just say rotate that 180 degrees?
I mean, just rotate only halfway though?
Yeah.
Yeah, like this way or that way though?
Either way, you
Okay.
still
I got it. It's that's the axis of flip flap and flip flap. That's the directions.
So well. Okay. I guess you can really do. You can't say you turn your up arrow left to make the down arrow right.
You could, but they would say, what do those
Yeah,
words
no,
mean
yeah,
again?
yeah,
Which one is
exactly.
which? It's up and down. We had our own words for that. We called them red and green, and you explained that red is opposite gravity and green is. So now we can translate. We have a dictionary. Okay, but still, like the linguistic teams called them up. This flip flap, left and right thing. We still haven't figured out how do we translate these words. I think it's okay to leave this one unanswered for now.
Okay.
Well, I don't want to give something away.
What you did say was interesting, Jason. I mean, it at least gave me a sense of distinction. There were a bunch of definitions that we were trying that had an extrinsic quality. That
Yes.
they had nothing at all to do with the. And then you said there were other properties that were intrinsic. It is in and of the thing itself.
Yes. It's like how many things did it have? We go to the fourth one. So we got some idea. In other words, everything we've described so far, I think we could successfully know that the aliens have made either this or that. They made, what?
Yeah.
The morning sickness.
Maybe we want this one, and they accidentally made this one.
See if it works. Does it work? We can tell.
Well, if they see, does that taste like a lemon or a lime? Right? So, at least as far as we've gone, I think it seems that we haven't been able yet to. We could make these two shapes, but we still haven't been able to distinguish them yet.
Could you tell them to make both?
Oh, they say, yeah, we made them both. Now, which one's the poison and which one? No. They just say, we're just curious about life on your planet. Which one is the one that, which one makes... Yeah, right. One of them made my pee smell. So Vernadsky points this out. He's like, because he had been, this was a question that was bugging him, too. He was like talking to mathematicians. He's like, is there some way to actually say left versus right? And they were scratching their heads. So he said, well, it seems like this is something that matters in life and doesn't matter in non-life. Not because it's hard and a difficult thing to do in math or physics, even using I keep thinking about the electricity magnetism thing. See, I just, but because it actually matters. So let's say when we were building these things up piece by piece by piece, if we build this in a laboratory, as in like not made by a bacteria or yeast or a plant or something, when we're making it in the laboratory and it comes time to put these two things on, it's like those aliens that have no idea what we're talking about. If you make it in a lab, you'll just get both. If you make it in a lab, you'll just get both. And you'll get 50% of one and 50% of the other. It's just each time that one is made, it just sort of happens. Outside of life. In life, you don't get them both. So like the amino acids in our body are left-handed. Carbohydrate starches are right-handed. Those words originally came from whether light passing. So going back to Pasteur,
Yeah.
had noticed that. So first, the thing was that people figured out about light being polarized, which is you could measure it by. I forget how polarized glasses. The way those things work is that when light bounces off of something at a really glancing angle, the light to the extent that it's like a wave, it's sort of like it vibrates in the direction of what it's bouncing off of. So if you're driving into the sun, the light bouncing off of the road has got a horizontal vibration. When you have polarized sunglasses, it's like they only let light that has a vertical vibration through. So that glare off of the road is just blocked.
Could we have said vertical and horizontal?
Yeah.
Oh. I thought
Well, let's still okay. So yeah, let's include those words. Sure.
You got so much. So they have up and down. But you still can't
Down,
define.
forward, back.
What about like if when you have like iron filings and you put a magnet underneath and it makes a spiral, and you could take that image of a spiral and put it vertically in front of you, and then if you follow the spiral up, then it will go to the right. Kind of thing?
I'd say, okay, yeah, let's just make sure we're doing this the same way. Which way do we orient our magnet? You'd say, oh, put the north up. It'd say, north? And say, yeah, that's the direction that compasses point on our planet based on the magnetic field it happens to have. And they'd say, oh, we haven't been there, I'm sorry. It's a tricky one. Because unlike positive and negative charges, north and south are... It's just based on what the Earth happens to be doing.
Right, okay. So a magnet wouldn't have it wouldn't be a magnet necessarily.
In other words, unless we can think of one, I don't know if we can think of a way of describing north and south in absolute ways. We got positive and negative with the nucleus versus the electrons. That's okay. I think electricity, yeah, we can say positive and negative. And the magnet's still a bit tough. At least so far. So the polarized light. Okay, so that's why it doesn't go. That's why people like to get the glasses when they're driving, because it gets rid of the glare like completely, which is great. Pasteur found out. Oh, and then some crystals will change what that angle is. So you could have light bouncing off the road, and if you hold a piece of quartz in front of your glasses, you will see the glare, depending on how you hold the quartz and what angle you put it at. And then when you put the quartz in front of your glasses, you'd figure out, oh, if I tilt my head a little bit, now the glare is blocked. Or maybe I have to tilt my head a little bit this way, either left or right. And I could say this piece of quartz rotates light either left or right. That's what left and right-handed originally. When I was saying like amino acids are left-handed or carbohydrates are right-handed, it's not always based on actual light rotation anymore, but that's where those words come from. So quartz is a crystal that rotates light's plane of polarization. Organic things in a solution also can do that. So sugar water. The sugar's not a crystal, it's just sugar water. And then again, light's coming off the road. I'm wearing my polarized glasses. I don't see any glare. And I hold a glass of lemonade or sugar water in front of me, and now the glare is coming through a little bit. The sugar water is tilted it to the right. And if I had a glass of liquid clear protein, it would go to the left. Egg whites would go the other way. And you should do this with sugar water and egg whites. So anyway, so this was interesting. Pasteur said, this is really interesting. He said the quartz is made out of building blocks that don't have any kind of spiralness to them. It's like if you made a spiral staircase out of cube bricks, if you demolished it and took apart the staircase, none of the bricks had any particular spin to them. The spiral staircase either goes up, counterclockwise or up clockwise, one or the other. The bricks don't. But for living things, each piece of it has an orientation. So it's like, in other words, the quartz, what the quartz is made out of doesn't have. Quartz is like a staircase that's made out of cubic bricks, but you put them together to make a spiral. And so, like quartz crystals, they come in both versions, left and right. And they're just quartz, nothing so different about them. Whereas the proteins in eggs are going to be all left.
You could say maybe they have the left and right, but they have it up at the top and the bottom. kind of like they have to be in that
With that
direction,
orientation.
or otherwise, yeah.
Yeah, it's kind of like they've got a direction of a helix.
Right.
Yeah.
Mm-hmm.
So, okay. So, anyways, that's what, so now, and Pasteur had done an experiment where he had an acid that came from making wine, and if you put it, he had a bottle of it in front of the thing, it would rotate the light.
Tannic
Obviously
acid?
to the left. No, it was
Tartaric?
yeah. If you made that acid in the lab, in other words, you could make this with wine. You got this acid. If you make it in the lab, you're actually getting both of these. So when he makes it in the lab, it behaves chemically the same because they're the same thing, but it doesn't rotate the light. Because when you made it in the lab, you got both of these, and they counteract each other. So what Pasteur did, is he crystallized it. He took it in the solution and let the water dry out and started to form crystals. Then with tweezers, he separated the left and the right ones with these little crystals, and then he showed, when I made it in the lab, it was really both of these. But if I pull them apart with my tweezers, I can actually make it tilt light to the left or the right. So this is an overall difference in living things. They intrinsically know left and right, and at least so far, we still haven't come up with a way to even describe left and right intrinsically, and neither has a chemistry laboratory because they can't make one versus the other. So like in the pharmaceutical industry, when they want to make one versus the other, they either have to do it with something living, the drugs are actually made by living things, or they have to use a building block to make the drug that came from a living thing. Like they don't just make the drug by like starting like atom by atom, but they'll say, this drug's based on something that we got from the something plant, so it's this one kind, and we'll build it up. Or when they sell it, it's just a mixture of both. And if it doesn't matter, if neither of them is dangerous, you can just sell them as a mixture of both, and no one cares. Ibuprofen is a mixture of. Ibuprofen is a molecule that has two hands, and when you buy the pills, it's just both of them. One of them helps, the other one just doesn't really do anything, but there's no harm in having it in it. And then some of them, they only sell one versus the other. So the only things that are able to affect it are things that are asymmetric themselves. So circularly polarized light can break up one and not the other, for example. But it also has a left versus right to it. So on these things that Vernadsky brought up, space, time, and energy and matter, there's an example of something about space that we don't have a formula for. In fact, we can't even really describe it. Left versus right, but it's a characteristic of living things. Left and right are intrinsically different, it seems, in life.
It seems that you can't describe life with space. Life becomes a characteristic of understanding. Life becomes a characteristic of understanding space now. Left and right.
Yeah, life brings in something that you can. Yeah. So you could say, I'll tell you what left is. It's the direction that light is rotated by DNA, or something like that. Say, okay. Of course, if the aliens have cells that are all different, so this is one of the questions. This is one of the questions. Is there something intrinsic about the left versus right, or is it just that life happened to be one versus the other when it started here, and then it just maintained that dominance?
Right.
Who knows? We don't know yet, but that's the characteristic of it.
Maybe the aliens actually don't
You
have
want to
left.
watch that
Like
voice
you can't
cast
identify
video?
with their hands. They don't have thumbs.
Space of
So, but like if they have a.
They still must have some way of giving each other driving directions, though. They're like, okay, well, shit, I don't know how to get to the house. I came to a T intersection and I just don't know what to do. Anyway, have a good time at the party. I'm going to turn around, but I can't decide how to.
They just have one way
The food is available, and people should. And there's the changes underneath people's sandwiches.
Yeah, for the lucky few amongst you, you'll find change under your sandwich. Don't leave a change. But it may be more or less than what you have coming to you. If it's less, I do apologize. I'm trying to make amends somehow. But your name is on the sandwiches too.
I don't know how organized. Oh, that was about what I had, that was the, I'll just say one other thing, which is the isotopes. It's just another, two things Vernadsky studied. One was this chirality, another was isotopes. So isotopes are basically the same chemically, but living things will pick one versus the other. It's very, I'm sorry, I should add two more things about chirality. So there was this Yuri Miller experiment, which was designed to create life out of lightning, and the idea was to try to imagine, ancient Earth. There's meteorites hitting, and there's lava and whatever, and could you create life out of that? So they put this stuff together and zapped it with electricity or whatever, and they did get some organic molecules. They were all mixtures, though. On meteorites, including this one, the Murchison meteorite, which I think landed in Australia, we find organic molecules in meteorites and comets. We found that. And they're also preferentially one versus the other. So this meteorite, there weren't any molecules that were only one versus the other, but it would have both, but it would have like 10% more of this one. Or 5%. I think the most was like 12 or 20% more of one versus the other. So, how did it wind up like that on this meteorite? Does that have something to do with, is that like a chunk of a planet that had life that has been sent to us from far away? Is there something about the universe as a whole that's actually got a handedness to it, or the galaxy?
Right, because Louis Pasteur was hypothesizing that it was something to do with the state of space, that the Earth was moving to a certain point, which would account for the appearance of life, right?
Right, yeah, so maybe it's like, maybe just we were hit by a lot of circularly polarized light, and there were both of these, but the direction that the light was polarized was like really absorbed by this one a lot and broke it apart, and so this one remained. And if there was at least a little bit of a predominance of one, maybe it would just take over. That's possible. So, it's sort of like, is there an intrinsic difference or not? Actually, in the 50s, some physicists discovered that there actually is a way to tell left from right. If these aliens are made of matter, not antimatter. It's based on the weak force. So, beta decay. If you've got a nucleus that emits electrons, based on the way you've oriented the nucleus with a magnet, they'll come out in one direction more than the other. And I'm forgetting exactly how that would, but you define left versus right. But it is interesting though that this one fundamental force, the weak force, actually it actually is different. So some people are saying, well, maybe that's the reason that life is the shape that it is as opposed to the other. So they do these like really tough computations and say, the amino acids in our body the bonds are stronger than the mirror image ones.
Well, yeah,
but it's a very tiny difference. It's like 10 to the negative 14. It's like almost nothing. So it might be nothing.
If they do have that experiment and they made out of matter and not antimatter, then it seems like we've established we seem to both understand the plane that we're on, or you're back against the wall or whatever. You could say, if the magnet is oriented along that axis, the electron's only going to go one way.
And now we can say, to make the electrons come upwards instead of downwards, the magnet for us points up as north. And then they say, now we know what north and south are. Now we can, say clockwise. Now we can, so yeah, if they're made out of matter.
You see them in cloud chambers all the time. Things are going off in different directions, but they're always the same.
No, that's not yet. The thing about how a magnetic field pushes it in one direction versus another, that's what you're bringing up before. It still has the problem of defining north versus, because you still have to say, well, which way is the magnet pointing in the cloud chamber? And then it's still left and right. Now we've got it, we get the magnet so that the electrons come up as opposed to down. We definitely know up versus down. And now if we know, now we can say north versus south. So then we could say, now put the cloud chamber, make the north point up, shoot an electron, which way did it go? That's right. Okay. Or left, or whatever. So that was that, and then just say one teasing thing about isotopes, and then
I wouldn't mind having a sandwich too. Isotopes also, it doesn't seem to matter. Oxygen 18, oxygen 16, oxygen 14, or carbon 14, or carbon 12. It's really not a big difference chemically, but in our bodies, the distribution of oxygen in our bodies is not like in the air that we breathe. So our bodies like, I'm going to get this wrong, like they like oxygen 18 more than 16. So the amount of oxygen 18 in our bodies is slightly higher compared to 16 than it is in the air that we're breathing. And
That's the way with carbon also.
carbon too.
Carbon 14 or carbon 12?
Yeah, I'm forgetting which way it goes, but they're different. It also is different in different organs in your body, different tissues. So that was another thing that Vernadsky was saying. Well, here's another thing where it seems like it doesn't really matter in physics or chemistry, but life cares. So maybe there's something to discover about the atom or the nucleus, and life will be the insight to that. And you'll never figure it out in the laboratory because life is the thing that's doing this choosing. So anyway, so the paper overall is really fantastic because he's got this whole polemic the whole time about why the Newton-Laplace thing of we can build up larger processes out of smaller ones. He says that doesn't work. We're making progress in science without using that. We're figuring things out in biology without explaining it all in terms of the molecules. So we don't need that outlook. We're making progress without that outlook. And you know, how can we come back with what we find out about all these things to then say, well, what's human society scientifically, as opposed to just starting from philosophy or something like that. It's like, as a scientist, how do we define what the human species does? That's not just in this paper, but anyway, it's a very good paper. It's also, I'm sure maybe do one of you guys have it in French too? I mean, if you read it that way, it'd probably be a lot better. But, L'étude de la vie et la nouvelle physique. It's
I haven't seen
yeah.
it.
It's on Vernadskys.fr. If you wanna, so you can. No. Come on. No. Okay.
Oh, great.
Can't be defined in terms of what came before. So think about these examples where you just had to develop a new language. Like you don't say, well, I'll tell you what the density of carbon is. You can't answer that. You realize that it's just not a legitimate question. You got to go somewhere else. So I'm going to play a video now. Actually, has anyone seen? I made a video like about a week ago on fusion. Raise your hand if you've seen that. Most people. Okay, enough people haven't that you're going to have to watch it again. So. But you get the unedited version. YouTube censored out the music and managed to remove it, so you get to. Yeah, it had a fake copyright violation problem thing, so you know. There was no actual copyright problem, but they don't know that.
We're getting the uncensored version.
We're getting the uncensored version. The one with music anyway. The only way mankind will exist in the future is through the mastery of controlled nuclear fusion. But fusion cannot be understood by enumerating its benefits or by calculating its electrical potential, although it is immense. The new quality of human civilization it will allow can only be adequately understood by looking at it in the long-term context of human development, from the physical world of the Stone Age to the chemical world of the Bronze and Electrical Ages, to the nuclear world that we have only just ventured into. By contrasting these stages of physical, chemical, and nuclear, we can understand the profound importance of developing a fusion platform, and specifically one powered by the rare isotope helium-3, found naturally on the Moon, but not on Earth. We'll start by going back in time a few thousand years. Years before the present, in the Stone Age, our tools and technologies were material, physical. Many tools were made from rocks, which might be chipped into better shapes, such as for sharpening, and other materials used for construction and tools were those found around us or made from them, such as fiber, wood, bone, shells, mud, and stone. If someone considered what a rock was made out of, the answer would be smaller rocks, and wood was made of wood. The characteristics of objects that were of value, besides food, were what we would call material or physical ones, such as strength, hardness, flexibility.
I was thinking of a few questions that I think Aristotle wouldn't appreciate very much. This thing about the middle term, all birds fly, ostriches are birds, birds fly. You might say, well, the problem was when you said all birds fly. Yeah. Because they don't. So, that's not a true statement. The thing is, though, that how would Aristotle deal with the need to change the language? When you've got a concept that you don't already have a way of describing, you end up always describing it in contradictory ways. Opposites exist. This maximum minimum was an example, but here's a few other ones. How many sides does a circle have?
360?
Only one.
Infinite. One, therefore infinite.
It doesn't have anything.
Well, sure, yes, it seems that it would be difficult to choose among these answers unless you were to say, well, really all of them are good, because, although in a way that none of them is really right. I mean, in other words, the circle doesn't have one side in a way that excludes it having an infinite number of sides. It doesn't have no sides in a way that excludes it having one. I mean, you might say, well, it doesn't have any sides. It's round. Sides are flat. It doesn't have any sides. You might say it has
You define sides as flat.
Yeah, or you might say, well, it has one side. Well, you might say it has an inside and an outside. It's got two sides. You want it to be tricky, but well, the front side, the back side, right? However you're looking at it, there's the left side, the right side, the top, and the bottom. So, it's when you ask a question that doesn't really make sense, you get more than one answer because the question isn't appropriate for understanding the thing that you're talking about. So, how about another one? There's this story about Archimedes, there's this eureka moment where he's in the bathtub, and there was this problem of trying to determine whether this gold bauble or crown, I don't know, whatever it was that was made for someone or another. The question was it really pure gold? Was there some other metal mixed in it? And Archimedes thought about putting something in water, and you could measure how much water it displaced, how much the water in the bathtub went up, or if you had it in a jar, you could measure how high the water went up. And that way you could figure out the volume of a strangely shaped thing. You could weigh it. So you could get its density, the relation between its heaviness and its size. And you could say, well, does it weigh as much as gold or is it lighter? And you could figure out how much of it was gold versus silver that way. So I just looked up on Wikipedia, and I found that the density of gold is 19.3 grams per cubic centimeter. The density of silver is 10.5 grams per cubic centimeter. Can anybody tell me
Durability, heaviness, size, shape, temperature, and so on. The changes we were able to cause were in large part physical reshaping and cutting and grinding, as well as movement. The simple machines of antiquity, the lever, the screw, the wedge, the pulley, and so on, these are physical machines, which could transform one kind of motion into another kind. For example, lifting a weight could be made easier by using a system of pulleys. More rope is pulled, with less effort, to lift a heavy weight a shorter distance. Or one mass could be used to lift another by using a lever. This table includes some characteristics of the physical world, the kinds of machines we had created, the characteristics of materials that we'd be thinking about, and the kinds of changes that we could bring about. Not included in this table is the application of fire, the use of which absolutely separated the human species as a creative species from all other forms of life. The first evidence for the use of fire goes back hundreds of thousands, or perhaps 1,000,000 or more years. With fire, man could cook new foods to make them edible and safer, harden rocks to make for sharper edges, fire clay, increase the flexibility of wood by boiling, treat textiles to create fabrics. We could see and protect ourselves at night. We could clear land. We could bake. After wood fire, the first change in our power over nature that was of a truly different physical type was seen in the birth of the Bronze Age. The Bronze Age, like the later Iron Age, took its name from advancements in making metals. Bronze is a combination of copper and tin, which requires a new kind of power over nature to create, and the resulting material, bronze, is stronger and more durable than either copper or tin. This is malachite. It's a blue-green rock, and it was the primary source of copper in the Bronze Age. As a rock, despite its unusual color, it's not so different physically from other stones. It's not remarkable by its hardness, its weight, its durability, its ease in chipping apart to make sharp edges. Yet, when a new kind of fire is applied to it, something amazing happens. This new type of fire is that of charcoal.
Eventually.
I mean, I don't know how you could, with like a straight face, do this thing about our sense of touch is what makes us intelligent. I don't know. To me, that sounds like the great lie or whatever. It's like, look, if people will go with this, you know, it's like just demanding people accept all of that, and it's like, how far can you push them? You know, here, eat some shit. You know, but feel it first. Here's a couple other ones. The atomic mass of chlorine. Kind of a weird one. If you looked at the weights of how about uranium? He said, what's the atomic mass of uranium? How much does an atom of uranium weigh? Does anybody know the answer for that one?
Yeah, we have to look at the isotope.
Which isotope, right? Now, no one would have asked that in the year 1900 or in the year 1890. That wouldn't have come up. It's, here's some uranium, and what does it weigh? There weren't different isotopes. Chlorine, why does it weigh 34.5 instead of a nice even number like most things do? Who knows? Maybe there's something very weird about chlorine. So again, yeah, right, it's a word that doesn't apply anymore because you're missing the concept of isotopes. How many terabytes of storage are in your brain?
I just upgraded.
Oh, you did? Oh, I got an SSD one. It's amazing. I remember things so quick now. It's good. The only trouble is once they go, they just go real quick. You know, you lose your mind. So, are you left wing or right wing? Is LaRouche, is he liberal or conservative? Is he Fox or MSNBC? Right? What is conviction or certainty? What does that feel like? What's the image associated with that experience in the mind? Because all mental experiences come with an image, a sensation. Is that a sensation that's like any of the ones that come from your senses? Does justice feel more smooth or more fuzzy?
It feels more purple.
Purple? Right. Yeah. So, you know, so those are some of the examples of the problems with it, the problems with logic, and then the fact that you can't really improve your language if you take that approach. Say, well, we've got ways of talking about things, and they'll serve us forever into the future. We can describe everything and use the language we've got right now, because how could we ever define a new term if it, I sort of ran out of time, what the density of carbon is? Feel free to use your phone if you want.
In which form?
Just like gold or silver, you know, they've got densities. So yeah, what's the density of carbon?
It's probably less.
Graphite? Or
Carbon.
carbon C.
Well, gold and silver, they're elements, right? So you know, carbon's an element.
I got
What's its density?
2,000, but this is kilograms per meters cubed. So I don't know if it works the same.
That's fine. What did you get for that?
2,250.
So that'd be like 2.25. Is that? Did anyone else get the same?
Kilogram per meter cube, yeah. 2.0 kilogram per meter cube. Oh, what are the units you're looking for?
Yeah.
Whatever. I mean, grams per cubic centimeter would be nice. If you get kilogram, 2.2670. Any other numbers?
Because like there's different density for graphite, diamonds, and all forms of carbon. So like could be
Right.
different numbers.
Well, that's a trick, right? So
You wouldn't measure the
there
density
isn't
of
an
carbon
answer to
grams.
that question, or there's multiple answers to that question, and it tells you something about carbon that's not true about gold or silver. I mean, gold's gold, silver's silver. Carbon, diamond versus graphite. You know, so the word carbon, you know, gold and silver sort of have they're words that are fulfilling two meanings. They're chemical elements. They're also physical metals. Carbon. People were immediately saying, well, what kind of carbon, right? Carbon's a chemical element. It's not a physical material. Graphite's a material, a physical material. Diamond is a physical material. You could go back to the Stone Age and say, you know, I mean, diamonds aren't just laying on the ground, but if they were, diamond, graphite, those would have words. There would be no word for carbon. You didn't have chemistry, you wouldn't have any idea that a diamond is the same thing as a piece of coal, would you? They're just not alike at all, really. So there's another example where the question doesn't have an answer, or it has multiple different answers, and that lets you realize that the way you were thinking has some room for improvement. If you ask what's the density of carbon, it's just not a good question.
I was just thinking, like, is there anywhere that Aristotle knew these questions just couldn't be answered, or just ridiculous?
I don't know.
Because like that has to come to his